Okay, so where we stopped? So I think I told you the intricacies and deep involvement of the one parameter bifurcation diagram. Okay. So what this bifurcation diagram can do, it is a fractal. It can exhibit chaotic dynamics. Okay. So it can exhibit fractal nature. It can exhibit different kind of bifurcations, and it can exhibit your cascade also, period doubling root to chaos. So many things it can exhibit. So to now we will go into a bit deep about the simplest invariant set of a dynamical system or a map that is known as a fixed point of a map. Okay, so the fixed point of a map is something interesting. Okay, and is the simplest example you can consider. Okay, so it is known as a fixed point, and fixed point is always of a map. Flows also you have a similar argument of like fixed point, but it is not referred to as a fixed point. It is referred to as an equilibrium point. Okay, equilibrium you assign to something to a continuous system which changes continuously. But discrete is like discrete. It is like t plus 1, t plus 2 like that, steps. So for maps, in this course, for the maps, we call it as a fixed point. And for flows, we will be referring to it as equilibrium. This is our terminology. This is the terminology. Okay. Fine. So fixed point of a map is the simplest invariant set. It's the simplest invariant set of the map. Okay. What is the simplest invariant set of a map? What is an invariant set? Invariant set is a set. Say X is a set, and you apply F to the set X, some function to the set X, and that set X, after application to that function, is still a subset of that set X. Then X is known as the invariant set. You understood that? Like suppose you have a set X, you applied the discrete map F to this set X, then it will be a region. It will be a region, right? You can think of this set X as a collection of a million set of points. And if you apply map F to those set of points, the output will be a set of points, right? So it will represent another region. Okay. And if that region is a subset of X, like this is F of X, right? Then X is known as the invariant set. Okay. X is the invariant set of the map F. Okay. Fine. Now this is a very general argument. That means it can work with any space, any metric you can work on. So, but here we will give a very simple definition. Okay. So a point definition, I mean on real line definition, this is for real line, line. Okay. A point x star. So on real line, it will be a point for one dimension. It will be a point. A point x star is said to be a fixed point of the map F if f of x star, if you apply f to that point, it will give you back the same point. I think this we discussed in the previous class. Okay, this we discussed in the previous class. Fine. Okay. So what is orbit? Orbit of fixed point? What is orbit of a fixed point? So orbit of a fixed point is the collection. It's the collection of the iterates. It's the collection of the iterates of the point. Okay, it's a collection of the iterates of the point. That means it's the collection of the iterates of the point, say x star. Can you tell me? So it will be x star, comma, the next iterate of x star, that is f of x star, then the next iterate of this, that is f2 of x star, so on. So can you tell me what is this iterate? What is this set looks like? Any ideas? Yes, it is just x star, just a singleton set. So orbit of a fixed point is a singleton set. Okay, orbit of a fixed point is a singleton set x star. Orbit of a fixed point is a singleton set, that is x star. Okay, fine. Now, graphically, how this fixed point will look like? Graphically, how this fixed point will look like? So graphically, the fixed point will look like, any ideas you have before I tell? So what you can do is you can plot the function y equals to f of x. Plot y equals to f of x, and this is y equals to x. This is y equals to x. Okay, and you plot the function. Then you will see the points where it crosses the y equals to x line represent some fixed point. Okay, because f of x is equal to f of x star is equal to x star. That means it is where this f of x will cross or intersect y equals to x, this straight line passing through the diagonal. Okay, fine. Now, now the question arises is, can any map f have a fixed point? What do you think? Can any map f have a fixed point? What is your thoughts on this? What are your thoughts? Can any map f have fixed points? Or there can be maps which don't have fixed points? What do you think? Hmm? Can there be a map which doesn't have fixed point? Hmm? What do you think? Hmm? Yeah. Any ideas? Can there be a map which doesn't have fixed point? Hmm? Any example? Yes. Good example. Yes. So that's what we need. That mind we need. That thinking, that thought power we need here. Okay. I told you the definition of fixed point. Then I gave you one question, which will be a googly question. Okay. So you should be thinking about it. Hmm? So consider map. Consider 1D map given by xn plus 1 is equal to f of xn, where f of xn is just 1 plus xn. Okay. So xn plus 1 is equal to 1 plus xn is our 1D map. Now what is the fixed point definition? So point x star such that f of x star is equal to x star. So f of x star is 1 plus x star, that is equal to x star. Can it occur? It can never occur. For any x star you take, x star plus 1 can never be equal to x star. So this can never happen. Never happen for any real value of x star. So that implies that the map f of xn, that is 1 plus xn, sorry, xn plus 1 is equal to 1 plus xn, does not have any fixed points. Okay, so you see how simple definition we turned into a very nice mind-boggling question. Okay, fine. Okay, okay. So anyway, after learning about a fixed point, so in dynamical systems and nonlinear dynamics, a fixed point, any invariant set. So any invariant set can be classified into two types. Okay, one is that is stable, unstable. Okay, that we'll see. Uh, and known as stability theory. This is known as a stability theory. That means if the fixed points are stable, suppose this is a fixed point and it is stable, suppose. So maybe so I have a notation that stable I mark it with a blue dot, unstable I mark it with red. So stable, suppose x star is stable, then what does it mean? It means that everyone will be attracted towards x star. Okay, that means what do we will be attracted towards x star? That means you have a point x naught, you apply the map f, it will come closer. You apply the map f, come closer, and move nearby. Anywhere you start, they will come closer, they'll be here. Okay, any point you take, they will come closer. Okay, so x naught again, they will come closer here. So they approach towards x naught fixed point, and it is known as a stable fixed point. But when this is known as a stable fixed point, what is unstable fixed point? Unstable fixed point is something like this. That means you have x star and it is unstable. So what happens is you have, suppose this one is suppose you take nearby, even x naught is this. Then what happens if you apply f? They will not come near to it. They will repel. They will get repelled away from it. That means this is f of x naught. This is another iterate. It will go away. They will go away. Anywhere you start, they will go away. Okay. Anywhere you start. So they will be moving away. So that is known as unstable fixed point. Okay, that is unstable fixed point. Okay. So when it is stable, when it is unstable, that we will learn soon. Okay, we will learn soon. But one of the most effective, methods, most effective graphical methods to understand about this stability, is about this cobweb diagram. Cobweb diagram is a cobweb diagram. So what is a cobweb diagram? We will see. Okay, but it will tell you where the iterates are going. Okay, where the iterates are going. So to do that, what you can do is step one. Maybe it will be easy to draw. Maybe. Okay. You have to draw a graph which has x and which has f of x, and think that maybe the graph is something like this. This is y equal to x. Think maybe the graph, maybe what we can do, which graph we can take. Any ideas? So if we take f of x equal to rx into 1 minus x, what will happen? Yeah, we can do something like this, right? Yes, this is a graph. Okay, this is f of x. So what is the step one in Cobweb is start from an initial point x naught. Start from an initial point x naught. Suppose this is x naught and you started from it. Okay, this is the initial condition. Now step two is you move vertically until you hit the graph x naught comma f of x naught. So move vertically till you hit the function curve. Till you hit the function curve. Okay, what does it mean? It means you move this way. And this is the point. What is the coordinate of this point, anyone? What is the coordinate of this point? X naught comma? Yes. You hit here. This is the step two. Okay. What is step three? Step three is travel horizontally from that point to meet the line y equal to x. To meet the line y equal to x. So let us move horizontally till you meet the point y equal to x. What is the coordinate of this point? Till you hit the curve, till the curve y equal to x. At what is the coordinate? No, you already know. This is y f of x naught. So this coordinate will be f of x naught. And since you are lying on y equal to x, the y coordinate will also be the same. So it will be f of x naught again. So it will be f of x naught comma f of x naught. Agree? Fine. What is step 4? How this happened? I don't know. Anyway, so step 4. So what is step 4? So when you reach here in the diagonal line, you can come back and put a point downwards. So what is this point? This is f of x naught. This is f of x naught. So can you understand that you started from x naught and on the x-axis you can know where the f has went. What is the role where the after applying f, where the point x naught is being pushed into. Yes. So now what you will do to this f of x naught? Same rule again, go back to step 1. From f of x naught, go back upwards till you hit the function curve. So move upwards till you hit the function curve here. Yes. Then what you will do? Move to the horizontal side till you hit the function y equal to x. Again come back. Okay. Again go up. Nowhere to go up. Finish. So this is the diagram. So if there is a fixed point, it will be like this. It will travel like this. If it is a fixed point. If it is diverging, you will see it will be traveling like this. Okay. If it is a period 2 point oscillating in between 2, you will see something like this. This point and this point. So this is our idea to see that in Python. Okay. So now you know. So move down, move back to x-axis and repeat step 1 to 3. So this is how you draw a cobweb, okay, of a 1D map. But what is the limitations? The limitations of a cobweb is can only be applied to one-dimensional maps, to 1D maps. Cannot be applied for higher dimensional maps. Cannot be applied to higher dimensional maps. That is 2D map or 3D maps. Okay, that's the limitation. Fine. So now we will go back to our Python example where we will draw the cobweb. So you can see this is the Python example here. We are doing the logistic map Rx into 1 minus x. R equal to 2.2 we have set. Okay. Can we decide some parameters? Note in your notebook and you should tell me this, the values of R. So let us go back. So yeah, can you note down these parameter values? R equal to 2.6. A fixed point is there. We will see how the cobweb behaves for these values. Okay. How you can make a transition from this one parameter bifurcation diagram to the cobweb scenario. Yes. So take R equal to 2.6, R equal to 3, R equal to 3.544, R equal to 3.545, R equal to 3.6, maybe 3.8, and also 4. All the values you note it down, and we will plot a cobweb for this. Okay. Let us go back. Okay. So what we are doing here, maybe I can show you the code later. I can share this. What you want me to tell? Yeah, tell me the first value, no? Okay. So it is running. Because we have taken a lot of points, so it is running. Okay. Yes. Now can you see something really interesting is there? So where we started, see this point is x naught. Actually, yeah, we started from 0.1. Our x naught is the initial condition. We started from 0.1. Okay. Now you see whether we have started from 0.1. Yes. This point is exactly at 0.1. What step we followed? Start from x naught, go back to the point where it will hit the function. Here it hit the function. After that, step 3, go horizontally till you hit the curve y equal to x. You hit the y equal to x. After that, again step 1 repeat. Go back to the function. Sorry, go back to the function here. Okay, hit the function, go back horizontally, go back. Same way you are doing, and you will generate this huge, nice graph. Okay, what this graph tells us, you can see it here. Now it is encircling, spiraling actually. Spiraling and converging to a fixed point. Exactly to a fixed point. And the fixed point is stable, right? Why the fixed point is stable? Because you started from this initial condition from 0.1 very far away from the fixed point, but still your iterates are getting attracted towards the fixed point, which is this. Why this is a fixed point? How I know? Because it hits the line y equal to x. And that's a graphical definition of a fixed point I told you. F of x star is equal to x star. This is the point where f of x and y equal to x have a common intersection. There is one more fixed point which you missed. Can you tell me? Of the map, there is still a fixed point which you missed. It's in the graph. Yes, exactly. 0 is a fixed point, but 0 is not a stable fixed point. Why? You started very close to 0, but still he did not even look at 0. He got repelled from 0 and went towards r minus 1 by r. That is the other fixed point. So in this case, the 0 is also a fixed point here, but is an unstable fixed point because, so do you want me to start very close to 0, like 0.001? Many might think that I have started at 0.1, therefore it is not converging. I will start from 0.001 and let's see where it converges. Okay. So we'll start from 0.001. Okay. Let us check where it converges. So yeah, done. Why this is? Yeah, you can see it here. I'm not able to go up actually. Can you see? Even if I started from 0.001, it still made a lot of steps, but still went there. So that means you can conclude from this graphical diagram that 0 is an unstable fixed point because it iterates. Cobweb diagrams are not converging to 0, but The other fixed point is a stable one because your cobweb diagram is converging there. Okay, fine. This is the case of a fixed point. Can you tell me the parameter value for the period 2 point? Yes, 2.3, 2.6, period 2 point. What is? It should come out to be a period 2 point. 2.3, 3. What is this? Okay, 3. Let us see. Yes, you can see something a different plot. Okay, but from this plot, we are not able to understand anything, right? I mean, it is going, but it is creating a mesh. I mean, it is going, but creating a mesh. So can we do some change in the plotting? Okay, we can decrease the number of iterations. 5,000 iterations to say 1,000 or maybe 100 steps. Then it will be clear. Yes, now it ran very fast. Yes, you can see now it is still converging to a period 2 orbit. Okay, maybe it is too much also. Can we reduce it? 40. Okay, still more. Yes, at least from here you can see how the cobweb is slowly entering into a periodic cycle. Okay, it's a period 2 orbit. Can you see why it's a period 2 orbit? Because it is intersecting in 2 points. Shall we make it 10? Maybe make it 10. Is it? Maybe it will be more clear. I think it is clear now. Is it? Somewhat. Okay, somewhat. But anyway, so this is a period 2 orbit. Can we go more? Can you tell me the next orbit, periodic orbit? Yes. Yeah. Then make it 20 maybe. Yes. You can see something different. Something different is there. Okay. So it's a period 4 orbit. Okay. Period 4 orbit. Now let us go to the chaos. Let us go to chaos. How chaos looks like. Chaos, of course, won't have any pattern to it. Okay. So here you can see that it is doubling like this. It is going, hitting here, going like this, coming, hitting here, and then back. Okay, it's a period 4. Let us make it 4, okay? Because at 4, I know that you have chaos. At 4, you know that I have chaos from the bifurcation diagram. But I don't think number 20 will be good. Let's make it 100 at least. Then you can see how unpredictable it is. Yes, so nice. Yes, quite interesting. I mean, yes, why it is interesting? I mean, it another interesting thing you can see is because it is occupying the full interval 0, 1. Some intervals were not occupying the full interval, but this is occupying the full interval 0, 1. I mean, you can see it is starting from 0 going till 1, 0 to 1. This is just a small number of iterations. This is how chaos looks like. But if I increase it even more, then you will be surprised. If I increase the number of points more, what is your first idea? Your first idea is, of course, they will overlap with some points before points. But the idea is no, they won't even overlap. Okay, they won't even overlap. So this is the idea where you can see. So you can see this one, let us run it. So here, yeah, let us see this point here, where it is. Oh no, we went to some other figure. Yeah, this is how it is. So you can see that it occupied the full interval. Okay, and you can see they are not even overlapping. They're not overlapping. The more and more you zoom in, you will see some separations between them. A tiny separation, but there will be separations. Okay, now I am not satisfied yet. I want to increase more because I can see that in between here it can still occupy those stripes. So what I can do, I can increase it till 5,000 maybe. It will take some time, but we'll see how it looks. Yes. So it has covered the full interval 0, 1. It has covered the full interval of 0, 1, and that's how chaos is known as the king. Okay, it can rule the full interval. Okay, it can rule the full interval, but your period 1 orbit or period 2 orbit will just take some points, 1 2 points, but chaos can occupy your full interval 0, 1. Okay, so if you want to, so this is how I got motivated to work in robotics. Actually, to be honest, this is how I got interested to work in robotics. Okay, so we did a work in robotics where this property we used in surveillance. Okay, so chaos is highly unpredictable. So I mean, like, drones can be fed the chaotic signal which can move unpredictably, so no hitter can hit and bring it down. Okay, your enemy partner is trying to bring it down, and but if it is moving like this, of course I know it will come here at one point, right? So I can hit here. So after 1 second it will come here and it will hit. But if it is chaotic, it will go like this, it will go like this, so you don't know where to hit, right? It is unpredictable. And why chaotic signals are good? Because it can occupy the full area. Suppose I want this room to be surveilled, okay, surveillance to be done, then I can use a 3D map. A 3D map, not a 1D map, but a 3D map. Means three coordinates. I can like one coordinate, second coordinate, and third coordinate, and it can move here and there, and you can never understand how it moves and predict also. So this is where you can do unpredictability analysis to drones. Okay, so with some electronics persons, we are doing this project before. But anyway, this is a good idea of Cobweb, uh, which I think is a very important tool for our purpose. Okay, let us be back to our computations. So let us see where we stopped. Okay, so now you know what is a cobweb and why cobwebs are so much important in our field. Okay, to understand stability. So without knowing about any mathematics about stability, from cobweb diagrams you can easily plot the stability part and understand which fixed point is stable and which fixed point is not stable. Okay, fine. So yeah, I think. Hmm. Okay. So now we will talk about stability of a fixed point. Now we will talk about stability of a fixed point. Okay, stability of fixed points. So, like, fixed points can be classified into two types. Okay, so fixed points, any fixed point, you can classify into two types. That is a hyperbolic fixed point and a non-hyperbolic fixed point. Okay, so we'll see when you call it a hyperbolic and when you call it as non-hyperbolic. Okay, so a fixed point, maybe here, a fixed point, a fixed point x star of a map F is said to be a hyperbolic fixed point if if the modulus of the derivative of the fixed point at the fixed point is not equal to 1. Okay, or you can say the derivative of the fixed point is not equal to -1 or 1. There it is known as a hyperbolic fixed point. Okay, so if it doesn't satisfy the case, it is known as a non-hyperbolic fixed point. Fine. Otherwise, it's non-hyperbolic. Otherwise, it's non-hyperbolic. Okay. So therefore, hyperbolic fixed points can be stable. Non-hyperbolic fixed points can be stable or unstable, right? So when you call hyperbolic fixed points to be stable or unstable, that we will look at first. Then we will go to the tiny case but important case of non-hyperbolic fixed points that can be stable or unstable. Okay. So hyperbolic fixed points. First, what are hyperbolic fixed points? So for hyperbolic fixed point, let x star be a hyperbolic fixed point. Okay, let x star be a hyperbolic fixed point. Let x star be a hyperbolic fixed point of a map F. Okay. And of course, you need to assume something. That is what you need to assume more. Any ideas? What you need to assume more? You need to assume that F be continuously differentiable, right? Because you are taking the derivative. Since you are taking the derivative, you have to assume that F prime exists. If derivative of F doesn't exist, then how you can compute the derivative of the fixed point and compute its value, right? So you have to assume the function F to be continuously differentiable. Yes. Then there are two conditions. If derivative of the fixed point of the function at the fixed point is less than 1, then the fixed point x star is asymptotically stable. Means this is a stronger form of stability. Okay, then the fixed point is stable. That means your cobweb will be close to converging to the fixed point. Yes. Then the next point is if f prime of x star is greater than 1, then x star is unstable. This you can actually prove. I'm not going into the proof, but this you can actually prove using the what do you call that? What do you call that? Mean value theorem. This you can actually prove using mean value theorem. Okay. I mean, you can do it. I mean, what does our mean value theorem tells? See, difference between 2x and you iterate it, the distance should be less when it gets mapped. Then only it will converge to a fixed point. So therefore, what you need to do, derivative the f of xn plus 1 minus f of xn is less than equal to some k xn plus 1 minus xn. I mean, if you remember mean value theorem, I don't assume you remember, but I'm just telling where this suddenly f prime of x less than 1 pops up. Okay. So you can know that this is basically the derivative, right? If you bring this guy to the denominator, it becomes a derivative. But note that if k is less than 1, then it implies that f of xn will approach to some x star, right? So therefore, if k is less than n, that means what is k? It means f of xn plus 1 minus f of xn divided by xn plus 1 minus xn is less than k. And this is nothing but the derivative. As you make n like xn plus 1 and xn close together. So therefore, you can see that this derivative is less than 1. Did I do something wrong here? I think okay now. Okay. So this is how this This is how you come to this condition actually. But I did not derive it much. I just told you the theorem. Okay, we can apply. So therefore, can we go back? Can we go back to our coding and see whether it satisfies the case or not? Yes. Let's go back to the coding part. So when you got to the fixed point, can you tell me the value? Say 2.3. I think at 2.3 you have the fixed point, right? Or 2 you have the fixed point also. I mean, you don't have to run for this number of iterations. Yes. Now my question is, can you compute the derivative of the fixed point? I mean, we compute the modulus of f prime at x star, and it should be less than 1 if it is stable. Okay. Now, can you compute the derivative here at the fixed point? It has to be less than 1. Okay. You can see almost it is equal to 1 if you put a derivative. But since it is stable, I believe it to be less than 1. Okay. So, I mean, graphically also you can check that why we resort to the derivative absolute value less than 1 as stable or unstable. Okay. So you can even, yeah, this is a good idea. This is a good idea. Can you check at 0, at x equal to 0, at x equal to 0, what is the derivative? Obviously greater than 1. At x equal to 0, what is the derivative? Can you see that at x equal to 0, I cannot draw on this, but at x equal to 0, you have to put a tangent. If you put a tangent, it will be the derivative, right? If you put a tangent. So if you put a tangent, it will be like this, right? If it will be like this will be, the slope is 1. The slope is 1. This is y equal to x, slope is 1. So if you put a tangent, it will be obviously greater than 1. The slope is greater than 1, right? If the slope is greater than 1, what does it mean? It is unstable. And indeed you see that it is unstable. It is unstable. But here you can see, in this plot, you can see that if you put a tangent here, it is almost close to 1. It is almost close to 1. Or like less than 1. You can check. And therefore it is stable. Is it clear? Or any doubts? Any doubts? Is okay. So here you can see that you can understand why the fixed point is stable and unstable just by looking into the graph. Just by plotting the cobweb. That powerful it is. Okay. So what we are doing is we are juggling in between two things. We are juggling from the math and we are juggling into the coding, and we are actually seeing the math is true, and then we are actually converting into the coding and checking that yes, it holds in coding also. So we are going hand in hand, like numerics and coding side by side. Okay. So one small exercise before we turn it off today. Okay. And we will start next class with non-hyperbolic fixed points. Okay. What is stability? What is not stability? But before that, I will give you one small example to do. That is, consider the 1D map. Say, consider this 1D map xn plus 1 is g lambda of xn, that is 1 minus lambda xn square. This is the 1D map, and it is defined on minus 1 comma 1. Okay. And lambda belongs to 0 to 2. Okay, fine. Now your job is to find the fixed points. Find the fixed points of g lambda of x and their stability. Can you do it? Yeah. This is a question. And this kind of questions you can expect also in different tests and exams. So since you have to compute fixed points and also their stability, it can be like something like 10. Okay. Yeah. So I suggest you do it now.